Hey everybody, Jonathan here. In this video, I'll be talking about section 11.1, which is all about sequences. So sequences, the book says you can think of them as a list of numbers, but it's actually better to think of them as functions. It also says they're functions. Instead of writing the input as x, we write the input as n, and the reason for that is that we're considering the domain to just be the natural numbers. So the, integers 1, 2, 3, and so on and so on and so on. So, and instead of writing f of n, we write a sub n instead. And then there's all this stuff about the notation, but look, literally all these sequences, they're just functions, except where instead of having x's, we have n's. Now there's a lot of advantages to this approach because there's a lot more things we can do with natural numbers than we can do with arbitrary real numbers. For example, we can make a sequence minus 1 to the n. Now any sequence can be graphed because sequences are functions, except with functions you'd get all real numbers, or most real numbers typically. So you'd get these curves. With sequences, you're just going to get a bunch of dots, basically one dot over each natural number value. So one new function that we could not do with real numbers is we could have the sequence minus 1 to the n. So that makes perfectly good sense for any natural number. Minus 1 squared is 1, minus 1 cubed is minus 1. In fact, it always bounces back and forth between minus 1 and 1. What if you try to do this with real numbers? Well, in here in Desmos, I've tried to graph the function y equals minus 1 to the x, and nothing is showing up. The reason for that is you can't do minus 1 to most rational numbers. For example, minus 1 to the 1/2 would be the square root of minus 1. You don't get a real number, and it's not even defined for irrational numbers. So the graph here is nothing because pretty much nothing, just about nothing, is in the actual domain. It only made sense for the integers. Another function that we can only do with natural numbers is the factorial function. I assume you've seen it before. N factorial for any positive integer is n times n minus 1 times n minus 2 and so on and so on down. In fact, it's even defined for 0. 0 factorial is 1. So if we graph the factorial function, it's not surprising that this gets really big really fast. Notice the vertical scale here is different. So 2 factorial is just 2, 3 factorial is 6, 4 factorial being 4 times 3 times 2 is already 24, 5 factorial is 120, and then I can try and zoom out further, but you have to zoom out pretty far to even see the next one because the factorials get big so fast. But the point is that this is a function that is only defined for natural numbers and not for real numbers in general. Now something we want to be able to do with sequences is we want to be able to take their limits. And here's the definition of the limit of a sequence, but in simpler terms, the limit of an equals L if an gets arbitrarily close to L by making n sufficiently large. And if this sounds awfully familiar to the language we used for limits for functions back in Calculus 1, it is familiar. In fact, this is exactly the same as taking the limit as x goes to infinity of a function f of x. So as a result, you can use all of your knowledge about limits of functions to find limits of sequences. So looking at some of the sequences we saw already, here's the sequence n over n plus 1. If we want to find the limit as n goes to infinity of that, it's just the same as taking the limit as x goes to infinity of x over x plus 1. And you might remember there's various ways of doing that. You can use your knowledge of rational functions. You can do L'Hopital's rule, but you get the limit to be 1. And sure enough, if we go ahead and graph the sequence, then as you can see, these numbers are getting really close to 1 as n gets larger. I can even zoom out a little bit. And so let's see, horizontal zoom out and making it bigger. They get closer and closer to 1, kind of indistinguishable from 1 after a while. So basically, if your sequence has the exact same definition of as an old school function, then you find the limit the same way as you would for that function. However, for our newer functions like minus 1 to the n and n factorial, for those functions, then we often have to use the squeeze theorem. The squeeze theorem for sequences is identical to the one for functions. Basically, if all the terms of one sequence Bn lie between the corresponding terms for a sequence as an and cn, and the limits of the an and cn are the same, then the limit of Bn is going to be that same limit. And here's a nice picture of it where the bn's in red, you see they're trapped between the an's and the cn's, and the an's and cn's are all getting close to each other, so the bn's get squeezed and have to converge to the same thing. In fact, we can use that to prove this very useful theorem that if the limit as n goes to infinity of the absolute value of the terms of a sequence is 0, then the limit of the terms of that sequence is also 0. And we can see that immediately from the squeeze theorem, because it's always true that no matter what an is, minus the absolute value of an is less than or equal to an is less than or equal to the absolute value of an. So if the limit of the absolute values of the an's is 0, then both this part and this part go to 0, so the middle part goes to 0 as well. And the book does a lovely application of this when it finds the limit as n goes to infinity of minus 1 to the n over n. So if your sequence has minus 1 to the n as part of it, then you can't relate it to a real valued function because minus 1 to the n doesn't make sense for real numbers. So, however, if we just take the absolute values, you get the good old feature sequence 1 over n, and of course that limit is 0, so by that previous theorem, the limit of minus 1 to the n over n will also be 0. So one final result, which really could have been made for functions, but we never did, is the monotonic sequence theorem, which says every bounded monotonic sequence is convergent. And let's see, bounded just means that all the terms of the sequence lie between two real numbers. So it has an upper bound and a lower bound. In the sequence pictured here, the upper bound is L. Monotonic just means the sequence is either increasing or decreasing. So all the terms here, you see they're getting a little bit bigger. So if you have a bounded monotonic sequence, then that sequence has to converge. Basically, the proof of that, which is a bit beyond what we would do in this course, despite what they say here, is that you take the least upper bound, and then it's going to have to converge to that least upper bound. And as you can see, they're going to get closer and closer, and sure, the limit will be that. So this is something we didn't worry about with functions, but it's going to come up a lot once we start talking about series. So the rest of this chapter, where we'll be invoking the monotonic sequence theorem a lot. All right, that's all. Have fun with the exercises.